Hello, Math 21 students. Welcome to the first lesson about subspaces. Part number 1, Introduction to Subspaces. Before we move on to the next page, please don't be scared by the word subspaces. The truth is, we've seen subspaces all the time since week number 2. Do you remember one of the homework problems had find all solutions or find all vectors in the domain that were mapped to the zero vector in the codomain? All vectors as a set in the domain that map to the zero vector in the codomain is an example of a subspace. So you kind of know everything from before. Do you also remember we talked about range of a transformation? Let's say the domain contains all vectors living in R3. And let's say our matrix looks like this from one of the homework. Then surely all vectors in the domain were mapped to a plane in R3. Everyone, all vectors in this range of T is also an example of a subspace. So please don't be scared by the word subspaces. You know everything you need. One more time, everyone. Range of T is a subspace of the codomain in this case. But it doesn't necessarily have to be codomain all the time. Subspace can live in the domain. This line in the domain is also a subspace of the domain, which means R3 again. This kind of subspace in the domain has a special name. It's called kernel of T. Basically, solution set of AX equal to 0 for Math 221. So once again, these vectors that were mapped to the zero vector in the codomain form a set. And this set has a special name, which is called solution set of this homogeneous equation, which is equivalent to, say, kernel of T if T is defined to be AX. Do you understand? So we've seen two basic examples of subspaces of some Euclidean spaces. Before we move on to the next page, let me tell you 3 characteristics of a subspace. These 3 conditions are very important for today's lesson. Listen carefully, okay? The first condition that you have to notice is that the zero vector in the space must be included in the set. Like this, 0 must be included in the set. Also, if you choose 2 random vectors in the set, their addition, u plus v, must also be included in the set. At the same time, do you remember? After the addition operator, we learned scalar multiplication. Scalar multiplication of a vector, this vector multiplied by another vector, and so on, must also be included in the set. If you satisfy those 3 things, then surely we can call the set as a subspace of some Euclidean space. Does that make sense? Just imagine this set as well. This set is entire xy axis, not just a positive region, okay? Just imagine this is the entire xy plane, okay? Surely, zero vector is contained in the set. At the same time, if you have 2 vectors living in the set, their addition must also living in the set as well. Do you understand? By the parallelogram law. So, u plus v must be living in the set as well for any choice of u and v in the set. Similarly, scalar multiplication of a vector must also living in that same space. If you satisfy those three conditions, then we can call this is a subspace and this shaded region is also a subspace. Condition 1, 0 is always in a subspace. Condition 2, the vector added by two random vectors. When I say random vectors, mathematically, two arbitrary vectors in the space is also a member in the subspace. Do you know what this means? It means we pick two random vectors in S and add them up. If u plus v is also in S, then we are happy. If u plus v, which is the red arrow, is also living in the plane, then we are happy. That's what I'm talking about for condition 2. Condition 3, scalar multiple of a single random vector in the space must also a member in that space. Do you understand? Scalar multiple of some random vector u must also living in S. If you can satisfy this condition, and then this condition, then you can call that particular space as a subspace of Rn, which is a Euclidean space. Do you understand everything so far? If so, let's have some more fun with the subspaces in the next part of today's lesson. Introduction is completed. Thank you and see you soon in part 2. Part number 2, we study more about subspaces. As a warm-up, let me give you 2 examples where one is a subspace and the other is not a subspace. This line living in R2 is a subspace. This line living in R2 is not a subspace. Can you pause the video and tell me why this is a subspace when this is not a subspace? Once you're ready, continue the video to listen to my explanation. It's gonna be really quick, short answer. This guy satisfies the 3 conditions. The 0 vector is living in this set L1. If you pick arbitrary vectors if you pick some random vectors u and v and add them up, still the result vector lives in the set L1, right? Similarly, a scalar multiple of u still follows the line, which means this set L1 contains all the vectors that is multiplied by u. So altogether, this L1 is a subspace of the Euclidean space R2. Now, this answer is so easy. Why is it not a subspace? The first condition, 0 vector, is not in the set L2. Therefore, this line L2 is not a subspace. We're about to do some examples in part number 3. And you have a feeling that we need to check first condition, second condition, and third condition to determine whether a set is a subspace or not. As a quick review, we're going to check whether 0 is in S, whether u plus v is in S, whether cu is in S. Once you complete checking those 3 things, which is right here, then you can call S is a subspace. Does that make sense? Honestly, depends on the question. It might take a longer time to follow these 3 steps than just using theorem 4.2. But we're going to study theorem 4.2 in part 4. Using this theorem saves a lot of time for only some cases, not all the cases. So please practice how to use these steps in part 3 of today's lesson. Part 3 is about examples. Thank you, and see you soon with part 3. We're going to have some fun with examples. Part number 3, examples. The first example is related to something that I mentioned earlier. Do you remember when we talked about this? Ax equal to 0, and then the key word is solution. I'm going to talk about the subspace involving solutions to this homogeneous equation, because you guys know how to use reduced echelon form. Here's the first example. Suppose we have this kind of linear system. The first question is related to week number 2 stuff. Find the general solutions to the system, to this homogeneous equation. Because it's a homogeneous equation, we have either trivial solution 0, 0, 0, or we have infinitely many solutions. So let's find out using augmented matrix and reduced echelon form. Okay, here's our augmented matrix, and you can pause the video and check my reduced echelon form with yours. There you go, everyone. We've successfully figured out the general solutions to this system. X1 equal to 2 times by a scalar, x2 equals 3 times by a scalar, x3 equals that scalar. In other words, if you want to write this as a vector form, for this time, can I just change the scalars S1, S1, S1 as like A or B or T, something like this? Because these are just dummy variables for a scalar. Thank you. This is the solutions in vector form, and here's the general solutions. Now, here's the question. Let S contains all solutions in vector form, maybe I should say. In other words, everyone, our set S contains all vectors of the form 2 times by a scalar, 3 times by that scalar, times by that scalar. There are infinitely many choices, right, everyone? So this set contains many, many vectors, okay? Now the question is the set S a subspace of R3 or not? Just like we did before, in order to find out whether S is a subspace or not, we need to check whether 0 is in the solution set, U plus V is in the set, or CU is in the set. So let's check those 3 things. In case anyone is confused by S containing all solutions in the vector form, let me picture what's going on here. Imagine S is a box. Box contains all solutions of the form 2A, 3A, A. Everyone, if you choose A to be 1, 1, 1, then surely the vector 2, 2, 3, 1 is in the set. Do you understand? Similarly, if you choose A to be -1, -1, -1, then surely the vector -2, -3, -1 is in the box. And the most simplest number is, if you choose A to be 0, 0, 0, then this vector 0, 0, 0 is in the box. Do you understand the concept here? and many more vectors living in this box. Do you now understand what's going on with S containing all vectors of the solutions? Now the question that we need to answer is that, do you think this box is a subspace of R3? Yes or no? Let me reveal the secret. This box, which is a space, is a subspace of R3. Let me prove it to you by checking those three conditions. Did you notice that we have 0, 0, 0? The 0 vector is contained in the box. From here, we've set A to be 0, 0, 0. So set A equal to 0. Then we're happy to see that the 0 vector is in the box. Do you understand? Second condition. We need to pick two random vectors u, v from S. We have to use the word arbitrary vectors. Arbitrary vectors means u looks like this: 2a, 3a, a. U looks like 2a, 3a, a. Also, v has to have this kind of DNA. This DNA is 2 times by a scalar, 3 times by a scalar, and that scalar, let's call it that dummy variable to be b, b, b this time. Now we have successfully picked u and v in the box S. Okay? We have to check their sum, u plus v. Do you guys understand so far? We have the result vector as 2a plus 2b, 3a plus 3b, and a plus b at the end. Now, I have a feeling that I need to take out the common factor 2, I need to take out the common factor 3. Look at this carefully, everyone. We have 2 times a plus b. This means 2 times by some scalar, a plus b, 3 times by the same scalar, a plus b, and then just that scalar, a plus b, which means our resolved vector also has the same DNA as 2a, 3a, a. Therefore, u plus v must be a member of elements in this box. And similarly, we can check the third condition, which is a scalar multiple of u. C times by the vector u is c times 2a, which is this, c times 3a, which is this, and c times by a, which is this. Now I have the vector c, u. Now my goal is to check whether this guy also has 2a, 3a, a kind of DNA. Look at this, everyone. We have Ca, which is a scalar, Ca, which is that same scalar, and Ca, which means exactly that same scalar. This means 2 times by that scalar, 3 times by that scalar, 1 times by that scalar satisfies the DNA of the box S. Therefore, Cu is in the box. Altogether, we have condition 1, we're happy. Condition 2, we're happy. Condition 3, we're happy. Altogether, the general solutions form a subspace of the domain R3. Thank you. This is the end of the first example. Let's try another one. Here's the next question. Determine if the following subset is a subspace of R3. If so, we prove it using the three conditions from the definition. If not, we just give a counterexample, why not? Here, A and B are just some scalars, okay? Just like before, we have a box S contains these vectors. If you choose A to be, say, 1, B to be 0, we have one particular element living in this box. 0, 1, negative 2 is in the box. If you choose A equal to 0, B equal to 0, then 0, 0 minus 0, 0. Therefore, 0 vector is in the box, and so on. So now we have a feeling that this might be a subspace. So how about we go and check those three conditions? Number 1, if you choose A equal to 0, B equal to 0, then this vector becomes the 0 vector living in S. Now you guys know we need to pick two arbitrary vectors living in this box and add them up. Let's say the first arbitrary vector to be U that has this kind of DNA. Let's call it 0, A1 minus B1, negative 2 times by A1, instead of just using AB. And then the second arbitrary vector V to be 0, A2 minus B2, negative 2 times A2. And you guys know A1, B1, A2, B2, all of these variables are some scalars. How about we try to add U and V together? 0 plus 0 becomes this. A1 minus B1 plus A2 minus B2 becomes, and then negative 2 times A1 plus negative 2 times A2 becomes, and there you go. We now have the vector U plus V. Now we're going to play with this and try to show that this vector is a member of this box. We can collect A1, A2 together. Because we have a subtraction, we must have subtraction here. That means B1 plus B2. And finally, if you try to take out the common factor, negative 2 times A1 plus A2. Look, the scalars A in front must be the same as A at the bottom. Fortunately, A1 plus A2, A1 plus A2 here, both are the same. And then let's just color the other scalar to be B, which means another type of scalar B1 plus B2. So surely 0 with this and that, U plus V has the same DNA as all the elements in the box. This means U plus V is also a member in the box. And lastly, we check the scalar multiple of U. C times by 0 is just 0. And then we feed chicken C times by this and C times by B1. And then negative 2 times by C times by A1. And there you go. This scalar and this scalar are the same. That means it satisfies this DNA along with another type of scalar, C times B1. What does this mean? Our vector Cu also has the same DNA as all the elements in the box. This means Cu is a member of this box. Altogether, our space S is a subspace of R3. And just assume, everyone, I forgot to mention, S is the set containing all such vectors. So if you like, you can write it as a first sentence. If you like, write the first sentence. Let S contains all vectors of the form 0, a minus b, negative 2a. Then we can use S here, S here, S here. And therefore, our S is a subspace of R3. Thank you. This is the end of the second example. The first two examples, if you noticed, were examples of some subspaces, right? The next example might be something that is not a subspace. Here you go. Let S be the set containing all vectors in R2 on the x-axis and y-axis. Do you know what this means? We have x-axis, y-axis, and we have xy plane. Now, what this means is we're only considering the set containing vectors on the x-axis and vectors on the y-axis only. Not here, and so on. We are not going to consider vectors living in here, 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 here. So now we have this kind of space. Let's check if this set of vectors is a subspace or not. Number one, surely the 0 vector lives in the space. Number two, we have a feeling that if you choose a vector here, choose another vector there, then do you think this vector, using the parallelogram law, lives in the space or out of the space? If you said their addition is out of the space, then you're correct. So in order to prove that this is not a subspace, we just need one example that makes the statement false. How about we take mother, father vectors and then add them up? Do you think the vector 1, 1, which is kind of this one, lives in the set S or not? If you said no, then you're correct. Therefore, this is not a subspace. Thank you. These are all the examples that I wanted to go over with you in part 3. As a last thing for part 3 for you, there's a your turn question. Let S be the set of vectors of the form AB, where A and B are integers. Could you please highlight this word, integers, on your paper? And you guys know what integers are. You know, there are infinitely many choices for integers. Whatever from the left, -3, -2, -1, 0, 1, 2, 3, and so on. These numbers are called integers. So suppose A and B are scalars, but they are integers. Do you think S is a subspace or not? Here's the answer. Students, try to explain why S is not a subspace. Thank you. Once you're done with the your turn problem, take a little break and see you soon with part 4. In part 4, we're going to study very quicker way to determine whether a set is a subspace or not, but it only works for particular cases. Anyways, thank you and see you soon. Part number 4, using Theorem 4.2. This result helps us determine whether a set is a subspace of some Euclidean space or not. For example, the key word that you have to remember The key word here is span. Whenever you see the word span followed by some vectors in the set, right away this entire set is called a subspace. This method, theorem 4.2, works only the case where the set is spanned by some vectors. Take a look. Let S is equal to, which means the set is equal to span containing the vectors u1, u2 up to um in the Euclidean space of Rn. Then the conclusion of the result is that S is a subspace of Rn. Everyone, our goal is to show that this set is a subspace of Rn. And you guys know that whenever we want to prove a set is a subspace, we have to check the following three things. As you know, the zero vector must be in the set. Suppose we pick two arbitrary vectors in the set S. Their addition, u plus v, must also be in that set. And then lastly, scalar multiple of a particular arbitrary vector in S must also be in that S. If you can show these three things, then right away you have successfully proved that the set span of u1, u2 up to um is going to be a subspace of Rn. So now you have an idea how to prove such thing. Okay, everyone, if you're ready, let's go ahead and prove the first condition of subspace. For instance, we have to show that the zero vector must be in S. In order to show the zero vector must be in S in this particular case, as usual, you treat all scalars like 0 times u1 plus 0 times u2 plus ... plus 0 times If you choose all scalars to be 0, then surely that zero vector must live in the set S. Surely, if you set all scalars to be 0, so the zero vector is indeed a member of that family. Now, everyone, let's pick up two random arbitrary family members in the set S. One of the family member looks like C1 times U1 plus C2 times U2 plus ... plus Cm times by Um. That's one general family member in the set. Also, we can write another variables as a scalar like d1 u1 plus d2 u2 plus up to dm um to be another family member in the family. So we can pick two random family members like this. So the first sentence here says pick two arbitrary random vectors u and v in the family S. Then u and v looks like c1u1 up to cmum. For v, d1u1 plus up to dmum. So it looks like this. Now look at the second condition, everyone. We would like to check u plus v, whether u plus v is in S or not. So do you guys understand everything so far? We just add u and v together and hopefully show that addition of this vector and this vector also lives in span of these vectors. In other words, if we can show, after adding these two vectors, if we can show that the result is also a family member in the family, then we're happy to put a check mark for the second condition here. You guys can combine the like terms, C1 plus D1, U1 plus C2 plus D2, U2, and so on. Did you guys notice that? C1 plus D1 is just some scalar, right? So C1 plus D1 is just a scalar. C2 plus D2 is just some scalar. Up to Cm plus Dm is just a scalar. So this vector C1 plus D1 times U1 plus C2 plus D2 times by U2, this linear combination means this vector lives in the span of these vectors. Do you understand? Since C1 plus D1, C2 plus D2 up to Cm plus Dm are some scalars, U plus V is now written as a linear combination of U1, U2 up to Um. Because it's a linear combination, it means U plus V is a family member of the family S. Congratulations, we've checked the first condition, second condition of subspaces. How about we check the last one, C times by U? Everyone, instead of using C, I decided to use R. The reason is I want to use C1, C2, Cm for U right here. C1, U1 plus C2, U2, and so on. So I want to use different letters such as R for random scalar. R times by this vector C1, U1 plus C2, U2 up to Cm, Um. Now, I'm going to feed chicken R times C1, R times C2, R times Cm, and so on. Look, since R times C1, R times C2, R times Cm are just some scalars, this member is indeed a family member of the family S because it's written as a linear combination of U1, U2 up to Um. Since R times C1, R times C2 up to R times Cm are just some scalars, surely this member is a family member of S. Do you know what this means? It means U R times by U is in S. Look, first condition, zero vector is in S, U plus V is in S, and then scalar multiple of some random vector, RU, is in S. Altogether, what is our conclusion? The conclusion is the set S is a subspace of Rn. Okay, congratulations. This is the end of very useful theorem 4.2. Do you know why this theorem is so useful? It's because we don't have to check these three conditions and spend a lot of time solving one problem. If a problem is written as span of blah blah blah, then right away that set is a subspace of this Euclidean space Rn by theorem 4.2. So solving the next example will be piece of cake if you know how to use this, assuming you know how to prove it. Now you do. So now you know one additional very useful theorem. How about before checking whether 0 is in S, U plus V is in S, or some scalar multiple of U is in S, how about we check whether we can use the theorem 4.2 first so that we don't have to spend a lot of time repeating the same thing. So step 0 will be check if a set is generated by some vectors. Generated means, everyone, if the set S is generated by some vectors, in other words, span of some vectors, then right away S is a subspace by the theorem 4.2. Then you don't have to do further work. Then you're done. If a set is not written as a span of blah blah blah, then you have to do the traditional way. Step 1, check if zero vector is in S. Step 2, check if u plus v is in S. Step 3, check if the scalar multiple of u is in S, which means technically these processes again for that particular problem. How about we solve one example that is applicable to theorem 4.2, such as this question, everyone. So here's the second last example for today. Instead of checking the three conditions as usual, we're going to use theorem 4.2 if possible. Here's the question. Suppose S contains the vectors of the form 2 times by some scalar minus another scalar, 3 times by the second scalar, the first scalar plus 5 times by the second scalar. Our goal is to show that S is a subspace. Everyone, did you just what I said when I talk about the vector? I just said A is the first scalar, B is the second scalar. Whenever you hear the word scalars, you can maybe decompose this vector into two parts like this. How about we decompose this vector into two parts? 2a becomes 2 is the first entry for A, 0 for second entry, and then the third one is just 1. -1 for the coefficient, 3 is the coefficient for B, and 5 is the coefficient for B, so write it down. Look at this, everyone. A and B are some scalars. It can be any real numbers. Do you know what this means? It means this is a linear combination of the vector 201 and -135. If it's written as a linear combination with any scalars A and B, then you can replace this with span, the word span, like this. Do you know what this means? Our set S right here, which contains all elements, linear combination of these vectors, is a subspace of R3 by what result? By the result 4.2. Everyone, this is the end of the problem, except we have to find out what is the Euclidean space for this set. This set is a subspace of R1, 2, 3. We have 3 entries, so these vectors live in R3. Thank you so much, everyone. This was the second last example for today. In the next part of the lesson, I'm going to pick one textbook problem and give you one your turn problem from the textbook. Thank you, and see you soon. Part number 5, some textbook exercises. One of them, we're gonna do it together, and the last one, how about you pause the video and try to solve this by yourself. So here's the first question. The shaded region over here is not a subspace of R2. Explain why. This problem is very similar to one of your homework problems. There are many ways to answer, but please try to do similar to what I'm doing right now. Here's my tip. The idea is how about we pick some examples such as, one vector here and one vector here and so on, and show that this set over here, the shaded region over here, is not a subspace of R2. In order for this to be a subspace, you need to satisfy these three things. 0 must be in S. Everyone, do you think this space contains the zero vector? Yes or no? If you said yes, then you're correct. So this doesn't really help us proving that this is not a subspace, okay? It looks like it's a subspace at the moment. However, do you think U plus V is in S or no? What do you think? If you said no, then you're correct. Let's prove why. Maybe we pick one example, say in this direction, and call it the vector 2, 2, 2, comma 2. And let's pick another vector in that direction, say let's call it negative 2, comma 2. Tell me yes or no. Do you think after adding 2, 2 and negative 2, 2 gives us a vector in that space or no? If you said no, then you're correct. Take a look. By the parallelogram law or vector addition property, you end up having U plus V to be this direction over here in red. But you can clearly see that the vector U plus V is not in the shaded region over here. So this proves that this shaded region is not a subspace of R2. Thank you, everyone. This is the end of all the examples with me. Now the last one is this question, everyone. Before I let you go to solve this problem, let me help you a little bit here. Okay, let me read the question for you carefully. S is a box. This box contains vectors of the form v1, v2, v3, okay? But be careful, v1, v2, v3 are not like scalars that you know from before. Before, A, B here act like the scalars, A, B, like this. So it's easier here. But v1, v2, v3 are some numbers that satisfies the equation v1 plus v2 plus v3 equal to 0. This is different than before. This type of the problem is different than this type of the problem where you can just take out a scalar A, scalar B, and get the brand new vectors. The last question that you have to do actually involves with the entries v1, v2, v3, which satisfies the equation v1 plus v2 plus v3 equal to 0. Look, what is the most obvious numbers v1, v2, v3 that satisfies this equation? Maybe the simplest solution is 0, 0, 0, which is the trivial solution. Do you agree with me that v1, if v1 is 0, v2 is 0, v3 is 0, 0 plus 0 plus 0 surely satisfies this equation? Do you understand? Do you know what this means? The vector 0, 0, 0 must live in S. So this box S contains the 0 vector. Also, there are many, many other choices, such as if you treat v1 to be 0, v2 to be 1, v3 to be negative 1, something like that. Then surely 0 plus 1 take away 1 is again 0. So the vector 0, 1, negative 1 also live in the box. And similarly, 1, 0, negative 1, 1, 1, negative 1, 0, something like this. There are many, many more vectors that satisfy the equation and belongs to this box. Now, everyone, do you understand what I'm trying to teach you here? We're picking some vectors that satisfy the equation v1 plus v2 plus v3 equal to 0. This box has many, many vectors in it. Our goal is to show whether this box is a subspace of R3 or not. Number 1, everyone, if you choose v1 to be 0, v2 to be 0, v3 to be 0, surely the 0 vector 0, 0, 0 is contained in the box S. Congratulations, everyone. I have successfully proved the first condition for you. Right here, the first condition is 0 must be in S. Also, U plus V must be in S, CU must be in S. So your job is to show these two conditions satisfied by the question. Okay, please spend time solving the problem. And if you have any questions, please let me know during office hours. If you guys want, we can check your answer and my answer on Monday during the live lecture. You just have to remind me. Thank you and have a great day.